Hi everybody. This is our look at a style of question that I like to call delta H to H back to delta H. On its face, this is somewhat of a surprising kind of question because on the one hand, the question says, here's delta H, but then asks, what's delta H? Okay? It's not a trick question. Those two delta H's are going to be different numbers. It's never as simple as this is the delta H. Okay? A question is going to provide us with a delta H and a mass and ask us to solve for a second delta H. That's why I call it delta H to H back to delta H. The first time through, we're going to convert the delta H in the question to a molar enthalpy. We're going to take the enthalpy change and divide by the moles. But the first move, the moles, is going to be the coefficient of the chemical the question is about. The balancing number about the chemical we're focused on. Okay, N. When we're converting back to delta H, the enthalpy change is moles times the molar enthalpy. We're going to do mass over molar mass. We're going to use the mass from the question along as the molar mass to convert it into moles. And this molar enthalpy is our answer from the first step. So it's a two-step problem, but on its face, it seems a little bit weird. Here's an example. Given the following equation, if 1.60 grams of oxygen are consumed, how much heat would be released? And we have some sulfur dioxide reacting with oxygen to make sulfur trioxide, and there's the delta H. Let's just notice that a question gives us a delta H and a mass. Here they are. There's the delta H. There's the mass. It's important to notice that this is about oxygen. Okay? And we're being asked for a second delta H and asked to solve for delta H. Here it's how much heat would be released. Given a delta H and a mass, we're asked for delta H, asked to solve for the enthalpy change, how much heat would be released, how much heat is absorbed, how much heat is liberated, lots of different terminology possibilities. Okay? Let's see what we got to do. Take the delta H and divide by the coefficient of the chemical we're being asked to focus on. H equals delta H over N. The delta H, it's explicitly right there, negative 96.4 kilojoules. Negative 96.4 kilojoules. We're going to divide by the coefficient, the balancing number of the chemical we're focused on. This is a question about oxygen. It's balanced here with this half, which I'm going to use as 0.5. I take my time, I'm going to calculate it. Negative 96.4 divided by 0.5. No problem. Negative 192.8 kilojoules per mole. I converted the enthalpy change into a molar enthalpy, H. I have a second step. I'm going to do N times H to get back to the delta H. Only this, now I'm going to do mass over molar mass multiplied by my answer. Delta H equals NH. But I'm going to do mass over molar mass. The mass is 1.60 grams of oxygen. So I'm going to use the molar mass of oxygen, O2. That's 32.00 grams per mole. And that's multiplied by our answer. negative 192.8 kilojoules per mole. Let me type that in. Multiplied by 6 over 32. I get negative 9.64. That's the full answer on my screen. I haven't rounded it off or anything just yet. That's my raw answer. Let me go back to the question. 1.60, negative 96.4. Those are both 3 significant digits. Conveniently, my answer already has 3 significant digits. I just have to worry about the units. Kilojoules. There is a style of question that I call delta H to H back to delta H. It's a little bit strange because on the one hand the question says, here's delta H, what's delta H? But we're also going to be given a mass as part of the question. It's a 2-step problem. We're going to convert delta H into H using a balancing number, a coefficient in our first step. But the second time through, as we're converting back to the enthalpy change, we're going to use mass over molar mass. Watch those significant digits, watch those units, and I hope that helps.